this video I will discuss support vector machines with numerical example. Here I will be discussing linear SVM example. In another video I have discussed non-linear SVM example. The link for the video is given in the description below. So this is the data set given for us. We have 8 data points. Out of 8 data points, 4 are positively labeled data points and 4 are negatively labeled data points. So these are the positively labeled data points and these are negatively labeled data points in this case. So what I need to do is I need to first plot these particular data points, and then I need to identify the nearest data points on both the sides of this particular classes. So the first data point is 3 1, 3 minus 1, 6 1, 6 minus 1. So if you look at this particular thing, that is 3 1 is plotted here, 3 minus 1, 6 plus 1 and 6 minus 1. These are plotted over here. So these data points are positively labeled data points. Similarly, we have another 4 data points, that is 1 0, 0 1, 0 minus 1, minus 1 0. So this is 1 0, 0 1, 0 minus 1 and minus 1 0. So these 4 data points are negatively labeled data points. Now once you plot this particular data points, next we need to identify the nearest data point on either side of this particular data points. So if you look at this particular data point, this is the one data point which is nearest from negatively labeled data points, and these two are from positively labeled data points. So you can say that this is 1 0, we will label this one as S1, and this one is S2, that is 3 1, and this is S3, we will say it as 3 minus 1. So S1 is equal to 1 0, S2 is equal to 3 1, and S3 is equal to 3 minus 1. So this is the next step what we need to perform. So after this particular thing, this is how actually the graph will look like. This is the S1, this is S2, and this is S3. This particular point is from negatively labeled data set, and this is from positively labeled data points. Now whenever you write an equation for the hyperplane, this side it will be equivalent to minus 1 and this side it will be equivalent to plus 1. So that is how actually we used to write the equation. Now what we do here is for each vector, whatever the 3 data points we have identified, we used to augment one as a bias input. So that is what actually we used to do before we continue with the procedure. So first S1 is equal to 1 0. This S1 is converted as 1 0 1, that is 1 will be added as a one more dimension to this particular S1. That particular dimension is nothing but a bias. Similarly, S2 is 3 1, 1 will be added to it, it will become 3 1 1, and S3 is equal to 3 minus 1. Once we add 1 to this one, it will become 3 minus 1 and 1. So just to differentiate these two data points, S1 is the original one and S1 tidal is the data point after adding 1 as a bias to it. So similarly, S2 tidal and S3 tidal here. Here we have 3 data points which are near from either side of the classes. So what we need to do here is we need to calculate 3 variables, that is alpha 1, alpha 2, alpha 3, which will be used to calculate the weight vector. Okay, so if you want to calculate alpha 1, alpha 2, alpha 3, these are the equations we need to use. Depending on the number of nearest data points, these particular equations will change. So in this case we have 3 nearest data points, so we need to calculate 3 variables, that is alpha 1, alpha 2, alpha 3. Now the question is how to calculate it. So if you want to calculate alpha 1, we can use this particular equation, that's alpha 1, alpha 2, alpha 3. So alpha 1 S1 S1 plus alpha 2 S2 S1, alpha 3 S3 S1. So if you notice this particular equation, in this equation S1 is common and S1, S2, S3 are used for calculating or writing this equation. And this one S1 is common, so S1 is present on what side? S1 is present on the negatively labeled data sets. So we equate this particular equation to minus 1. Similarly, alpha 1 S1 S2, alpha 2 S2 S2 plus alpha 3 S3 S2. So in this case S2 is common, S2 is present on the positively labeled data set, so we used to equate this equation with plus 1. Similarly, alpha 1 S1 S3 plus alpha 2 S2 S3 plus alpha 3 S3 S3. So in this case which one is common? S3 is common. Again S3 is present on the positively labeled data points, so we used to equate it to plus 1 here. Next, what we need to do is we need to put the values of S1, S2, S3 in this three equations. We will get these equations here. Now once you get this particular equation, so what we need to do is we need to perform the normal you can say that operations over here, arithmetic operations. These are the two can say that the vectors, so we need to perform dot product between these two vectors. Between these two we need to perform the dot product, like 1 into 1, that is 1, 0 into 0 is 0, 1 into 1 is 1, that is 1 plus 0 plus 1. So that is the answer for this particular dot product. Similarly for this one, 3 into 1 is 3, 1 into 0 is 0, 1 into 1 is 1, that is 3 plus 0 plus 1. Similarly 3 plus 0 plus 1. With the same note we can calculate or we can simplify these two equations also. We will get something like this, that is alpha 1, 1 plus 0 plus 1, alpha 2, 3 plus 0 plus 1, that is 3 plus 0 plus 1, and alpha 3 is equal to 3 plus 0 plus 1. So this is the first equation. With the same note we will be getting the second equation here and then the third equation. So once you get these three equations, we need to simplify it again, that is 1 plus 0 plus 1 is 2, 2 times alpha 1 plus 4 times alpha 2 plus 4 times alpha 3, which is equivalent to minus 1, 4 times alpha 1 plus 11 times alpha 2 plus 9 times alpha 3 is equivalent to 1, 4 times alpha 1 plus 9 times alpha 2 plus 11 times alpha 3 is equivalent to 1. So once you get these three equations, what we need to do? We need to simplify these three equations so that we will get the values of alpha 1, alpha 2, alpha 3. We have three equations or simultaneous equations. Along with that we have three variables, so definitely we can easily solve these things and then we will get the values of alpha 1, alpha 2, alpha 3. So once you solve it, you will get the alpha 1 is equal to minus 3.5, alpha 2 is equal to 0.75, alpha 3 is equal to 0.75 in this case. Now once you get three values of three variables, what we need to do is we need to calculate the weight vector, that is W cap or W tidal, which is equivalent to summation of alpha I Si, where I is the number of nearest data points. So how many nearest data points we have in this case? 3 nearest data points. So this will become I will be 3 alpha 1 S1 plus alpha 2 S2 plus alpha 3 S3. So alpha 1 is equal to minus 3.5, S1 is 101 plus alpha 2 is equal to 0.75, alpha S2 is equal to 311 plus 0.75, that is alpha 3, S3 is equal to 3 minus 1, 1 here. So once you solve this particular equation, you will get 1, 0, minus 2 in this case. So W tidal, that is W vector, is equal to 1, 0, minus 2. So this one is after adding the bias. So now we need to differentiate bias and the actual weight vector. So if you differentiate it, third one is always the bias here. Okay. So what we do here is the actual weight vector is 1, 0 and minus 2 is the bias in this case. So our line equation or the hyperplane equation, y is equal to wx plus b, b is equal to minus 2 and w is equal to 1 and 0 here. So w is equal to 1, 0 and b is equal to minus 2. So once you get this particular the weight vector, we can decide where the line should be drawn. Because b is equal to minus 2, that is we need to consider it should be either on the first quadrant, you can say, and w is equal to 1, 0. What is the meaning of 1, 0 is x is 1, y is 0. It means that the line is parallel to y axis. If it is 0, 1, the line is parallel to x axis. If it is 1, 1, definitely the line will make 45 degree with respect to x and y axis. Okay, so in this case w is 1, 0, the line is parallel to y axis. So that is how actually we need to draw it with a bias, or you can say that the offset is equal to minus 2. So if you look at this one, minus 2 means it should be in the first quadrant, either it will be over here or over here. Because the line is parallel to y axis, it will be considered here, and then the line will be drawn parallel to y axis here. Now if you look at this particular the diagram, you can see here this particular hyperplane will perfectly divide the data, that is the negatively labeled data points and the positively labeled data points correctly here. Okay, this is how actually we will solve a linear SVM problem numerically. I hope the concept is clear. If you like the video, do like and share with your friends. Press the subscribe button for more videos. Press the bell icon for regular updates. Thank you for watching.